Hi, everyone. Welcome to our session. We are so thankful that you chose to listen to us today. We are going to present to you bioretention underperformance, the trials, tribulations, and some solutions that we could come up with. I'd first like to introduce you to our research team. Myself, Claire Bradley. I'm on the left in this picture. In the middle is Pam Daniels. On the right is Katherine Wolfe. And we had the pleasure to work under our faculty advisor, Professor John Tippett. We are 3 students from the University of Mary Washington. We are presenting to you our summer research. We hail from the Earth and Environmental Sciences Department, where we all have majors/minors. So quickly, I'd like to take y'all on a roadmap of what we'll be talking about, just so we're on the same page. The first is some background, why we chose bioretention, etc., research. Then we'll talk about our findings from our research and what we can conclude from that. Next is our case study, where we attempted to estimate the magnitude of some of the stormwater treatment lost throughout ineffective bioretention practices. Next is our recommendations that we could come up. And finally, we'll have a question and answer session for y'all. So some background on bioretention. Why do we choose bioretention? Why do we use it? Well, it is a very effective method. Pollutants such as nitrogen and phosphate, which as we know can really damage our waterways, as well as removing some heavy metals. Not only can it be really effective at these things, but it's also aesthetic looking. It can blend perfectly into a landscape. And bioretention is used with the Chesapeake Bay total maximum daily load, which is its goal with the EPA to remove these pollutants, or in a certain percentage of these pollutants, by the year 2025. With this goal in mind, you have to keep in mind that these earlier practices are now reaching 20 or so years old, and with this, they are experiencing some performance degradation, such as faulty initial designs and poor maintenance overall. So in this image that you can see on your screen, this is the 2014 monthly dissolved oxygen within the Rappahannock River. The lighter blue represents higher dissolved oxygen, and the red represents low dissolved oxygen. And this is one of the many reasons why this is really important to us. And it was really important to do this research because it counts as removing these pollutants from our waterways. And if they're not working as they should, then we need to do something to fix that. So our purpose and objectives: first, we want to assess the causes of their underperformance. And we wanted to also model this underperformance so we could estimate approximately how big of a problem this was, and then finally recommend some design and maintenance changes which would help prolong the lives of these bioretention cells. Next, I'll be talking about our methodology which we use to collect our research. I first want to start off by talking about 2 terms which will be used throughout the rest of the presentation. The first is an online bioretention cell. This is where water enters through an inlet. It goes in through the practice, and once enough water is in the system, it reaches a maximum ponding depth. And after it surpasses this maximum ponding depth, it will overflow into the overflow. The second type, which is a more recommended type, is an offline system. So water enters through the inlet, but once it reaches its maximum ponding depth, water is diverted along a curb and then goes into a drop inlet. Some of our site selection was largely based on its proximity to us at the University of Mary Washington in Fredericksburg, Virginia. And we also were blessed to have Stafford County give us their GIS layer, which had their bioretention practices within there. So largely our research was in this area, as well as some within the City of Fredericksburg and some in Spotsylvania County. This ended up totaling to be 109 sites. So, our field collection and data collection parameters. We based our collection parameters off of the Virginia Department of Environmental Quality Standards for Bioretention Practices, and I'll go over a few with you guys really quick. The first would be the general design practice. Is this an offline or online system, as well as its bioretention classification as specified by the VADEQ. Water flow. How is water moving within a system? Can it get into a system? How is it acting within the bed? And one last example would be the ponding depth and volume. which we measured by taking an elevation at the inlet, the outlet, as well as across the bed surface. So we went out into the field and we were able to use our cell phones to collect this data within an application called Survey 123, which is owned by Esri. This application really easily allowed us to make a GIS layer from this to see all of this data in one place. And we would look at the attribute table, see what was really standing out to us, and then be able to see what we wanted to assess further. Out of this, we would move this data into Excel, where we're able to create some of the graphics that we'll be showing you later throughout this presentation. Next, I'm going to turn it over to Pam Daniels, who will be further discussing our findings.
So thank you, Claire. Now I'm going to be going over our overall findings for the study. So to start, our study didn't really focus on any sort of social or socioeconomic aspects relating to bioretention function. But we do still think that there are some sort of relationships that might be super interesting to analyze in a future study. So we decided to do some preliminary research into some of these socioeconomic aspects. And the one that we looked into was whether or not there might be a relationship between the wealth of an area with a bioretention system and the actual functionality of those bioretention systems. So to do this, we started by using the GIS layer that Stafford County gave us of all the different bioretention sites in the county, and selected the ones that we were going to go to. And then using those points within GIS, we looked into the neighborhoods that were surrounding those areas. Then we opened up Zillow and we found where the actual sites would have been in the point layer, and analyzed the housing prices surrounding those sites as a determiner of wealth, since obviously wealth can sometimes be really difficult to determine. So we figured that housing prices would be a pretty good determiner in order to do that. After we had determined the neighborhoods that we were going to be looking for housing prices in, we took a sample of house prices based off of how many sites were clustered in that area, since sometimes there can be 3 or 4 sites in one little, and then we averaged the housing prices for that sample so that we had an average housing price and an average functional rating of the sites in that area. And then we took those values and we plotted them against each other on the graph that you see on the screen. And so as you can tell, it's really hard to kind of discern any sort of trend. This is probably due to the fact that we really only collected very basic data and did a very preliminary research, or did preliminary research into this topic. But we do think that this could be a really interesting topic for future research. And so that's why we're suggesting that maybe in the future, we try to include the age of the practice to see if maybe that has any sort of influence and include it on the graph as another variable, or we try to fit regression lines to these to see if it makes it a little bit easier to visualize any sort of trend. So for an overall summary of the data, up at the top, here is a graph of the functional ratings that we gave the sites. And as I mentioned earlier, the functional ratings were things that we gave on site. They were based on a number from 1 to 10, with 1 being the least functional and 10 being the most functional. And these functional ratings were generated both from our knowledge that we learned prior to the research of bioretention systems, as well as the overall parameters that we collected while we were on site and what we were able to determine from them. And as you can see from the graph on the screen, the majority of these sites fell within the moderate area of site functionality from about 4 to 8 or 4 to 7. So many of the sites that we visited weren't actually functioning at the frequency of factors that led to DEQ noncompliance. DEQ noncompliance just refers to how well these sites were able to comply with the specifications put forth by the DEQ for the codes for bioretention. And so the graph below is just detailing how often we came across the variety of factors that the DEQ puts forth as needing to be complied with for these sites. The 2 most common ones we came across were the lack of pretreatment and ponding depth. And it's very important with pretreatment to understand that there is a caveat with it, just because many of the sites that we ended up visiting were built at a time where the current regulations for pretreatment were not in place. So we believe this may also be a factor for why this was such a common issue within these sites. So to start with our actual findings, we're going to begin with side slope erosion. Side slope erosion is a big deal because when you have eroding side slopes, that sediment that's coming off of them has to go somewhere. and it'll end up in the bed where it may create an impermeable layer that'll make it very difficult for water to filter through. About 25% of the sites that we visited had some form of side slope erosion, and then from that number, we were interested to see how many of those sites with side slope erosion already present had slopes that were greater than 25%. And we found that 72% of sites with eroding side slopes had that issue. On the next part, we have short circuiting. It's important to mention that with short circuiting, it really only matters for online systems, just because online systems require that all water passes all the way through the system. So short circuiting is when you have the overflow unit placed directly in front of the inlet, so that all of that water that is coming into the system doesn't even get a chance to go out and filtrate. It all goes straight into the overflow. And about 11% of the online sites that we visited had this issue. And even though that is such a small number, because this issue causes it doesn't even get a chance to filter into the ground, just go straight into the sewer system, we still feel it's really important to include in this presentation because of the fact that it renders the system practically non-functional. So, for bare soil, we looked into two different aspects, surface crust and overall mulch depth. With surface crust, similar to eroding side slopes, surface crusting can create an impermeable layer that makes it very difficult for water to filtrate through and ultimately perform the function that these systems were put in place for in the first place. About 18% of the sites that we visited had some form of surface crust. For mulch depth, the DEQ specifies that these systems are meant to have at least 2 inches of mulch present on them. However, about 78% of the sites we visited had less than 2 inches of mulch, as you can see by that image right next to the statistic, where it's just dirt and gravel. Mulch is really important for filtering out toxic heavy metals that might come off of a parking lot and actually binding them in order to get those metals out of the water in the first place. Next up, we have pretreatment. And again, it's important to reiterate the fact that many of these sites were built before the current regulations were put in place. So that might be why we found a lack of pretreatment so often. But about 74% of the sites we visited had a lack of pretreatment. And pretreatment is really important for filtering out bigger particles like sediments or debris that might block a system and render it non-functional or less functional. So even with that caveat, we still felt it was really important to include it in here just because of the importance that pretreatment plays in the system. Median compaction is our next factor here. And about 46% of the sites that we visited had a compaction level of greater than 300 psi. Now we chose 300 psi because some of the literature that we were reading through states that 300 psi is a pretty good threshold for how well plant roots can penetrate the ground. And since plant roots are plants themselves are a pretty important factor in bioretention, we felt that that would be a pretty good number to use as the threshold for this factor. And as you can see, examples of this median compaction or high median compaction in these images is clay showing up relatively shallow in the system, as well as a soil sample with so much clay in it and so compact that it practically looks like a wine cork. So let's step out of things for a minute. Ponding is probably one of the most important aspects of bioretention in the first place. It ultimately tells you how much water you truly can filter within the system and how much of a difference you're actually making. And about 40% of the sites that we visited were underponded. We calculated underponding based off of actual ponding and desired ponding. Actual ponding comes from our bed surface elevations that we took when we were on site with a rod and a survey level in order to see what the elevations of the bed themselves or the bed itself actually was. The desired ponding comes from the values we calculated based off of what the DEQ specifies these different types of sites should have for ponding. And so, since ponding is so important, if you have a tilted bed, like many of these sites did when they were underponded, you're ultimately reducing how much water you can actually treat, which then reduces the functionality of the system. Next up, we have inlet blockages. So inlet blockages can form in different ways. They can be from debris and grit, as you can see on that image, or they can be from a lack of elevation drop at the inlet, as you can see on the left, where the riprap is piled up so high that water actually doesn't have an easy enough time getting into it. And about 50% of the offline systems we visited had this issue. It's the most important for offline systems just because of that fact that there is the option for water to be diverted into a drop inlet if the initial inlet is blocked. And so this is especially a big issue when you have both problems or when you have an elevation gain at the inlet, which causes water to pool. Water is already holding sediment or debris in it, so then when it pools, it drops that debris, only exacerbating the issue. And so from there, I will hand it off to Kat to go over our case study.
Thank you, Pam. And now I will be going over our case study. As Pam mentioned, 32% of inlets for offline systems experience blockage within our inlets. And so we asked ourselves, what is the impact of inlet debris berms on bioretention treatment? To reword this, at what height of these berms are affecting how much water is able to enter these practices? So we decided to look at a previous site that we had studied, a previous offline system, and create a topographic map of this area. We went out with our TopCon level surveyor and a rod and shot different elevations throughout a parking lot to create a grid. And from that grid, we were able to create vector points. And those vector points were put into ArcGIS. And in ArcGIS, we were able to create a digital elevation model. And then from that digital elevation model, we were able to create different subcatchments within the area. Those subcatchments were put into a hydraulics hydrology program called PC Swim, where we were able to create a hypothetical system which the water flowed through. This is a modeling procedure, so there are a lot of still questions that we aren't able to answer, but through modeling we were able to potentially get hypothetical analysis. So first we put our subcatchments in, and we defined different variables within the system. Like the gutter dimension, the resistance to flow at different points based on pavement or different textures. And then we also did pour points where sheet flow turned into channelized flow at the gutter. And then we ran different storms through our hypothetical system, varying in duration and intensity. And then from all of the different storms that we ran through our system, we took that data and put it into Excel to create flow bypass hydrographs. So looking at this hydrograph on the next slide, there are some points that I want to go over. So as you can see, on the x-axis is time and y is discharge. And as you can see, the orange here at the bottom is around 0.1. So that is the discharge of flow at that period of time. And we know, and in this example, that the height of our berm is 1 inch. So we have 1 inch of discharge and the berm is 1 inch. So we know that water isn't going to be able to bypass into this system, or isn't able to enter this system and bypasses into the drop inlet. Now, the light blue in the graph is the water quality volume. As we know, the water quality volume is that first half inch of a storm, that first initial flush that contains most of those nitrates, phosphates, and heavy metals that we're trying to remove from the water using these sites. So as you can see here, a lot of the water quality volume is being completely diverted. And not being, as you can see, a lot of the water quality volume is bypassing and not being treated at all. So for our case study findings, we turn this into bar graphs. So here we have a 0.5 debris inlet and percentages of the water quality volume that weren't able to be treated in the system. So for a 0.5 inch berm, 13 to 55% of the water quality volume isn't being treated. This is so significant because it shows that for such a small amount of debris within the inlet, we are missing a huge part of the water quality volume that we want to be treated. Taking this up a notch, looking at an inch high berm, you're looking at 45 to 99% of the water quality volume. And this is so significant because when we were out in the field, we saw 3 inches of debris within the inlets.
Thank you for that, Catherine. I'll be talking about ponding depth. As Pam mentioned, ponding depth can largely affect the way that a bioretention cell can treat its water based on the amount of volume that it can intake. So, our recommendation is to ensure adequate ponding depth across the entire bed surface at construction and at inspections. Strongly sloped beds reduce the ponding volume and therefore affect its efficiency to intake water. And we believe inspections should incorporate bed surface elevation readings across the practice to ensure that the surface is level. Our next recommendation is about side slopes. We recommend that there is extra stabilization of side slopes greater than 25%. In some areas, it's not possible to have a reduced slope, so we recommend that there is sodding or armoring along the side, or incorporate topsoil, which would encourage the growth of grass within these places. Then we'll talk about elevation drop. This is most important at offline systems because, as Katherine discussed, we can see the magnitude of what happens when there is no elevation drop at these inlets of offline systems. So we recommend that there is an adequate elevation drop at inlets on offline systems to prevent flow bypass, and we recommend avoiding this by ensuring that there's at least 3 inches of elevation drop between the pavement and the top of the riprap.
So for inlet debris, we simply suggest that if there is debris in an inlet, it is cleaned. This can happen at the inspection stage, whenever the inspectors show up to evaluate the functionality of the system or how well it looks. Because of the fact that if this debris is present, it can cause a significant bypass of the water quality volume, as we saw in the case study that Kat presented. So overall, we simply suggest that inlet debris is cleared from the inlet so that water can properly filter in. For mulch depth, it is important to ensure that there is a sufficient mulch depth in the first place. This does not mean excess mulch, and it does not mean insufficient mulch. It means that it's just the right amount that can help filter out the water without impacting the overall functionality of the system. It's super important for pollutant removal, so it's important to have in the first place. But if you have too much, it can ultimately impact the system and make it more difficult for water to filtrate through in the future. So we should at the very least enforce the minimum mulch criteria of 2 inches and try not to go too much over that. Short circuiting, again, it's important to mention that short circuiting is really only important for those online systems where water has to pass through the whole system itself. But for those systems that already have an issue with short circuiting, we suggest going in and retrofitting those overflows and finding ways to allow water to move around them instead of directly into them. This can be done by raising the overflow higher up so that there's a bit of a barrier between where the water would normally flow through and where it can now flow through, so there's a bit of a wall that it goes around. And this would actually restore the functionality of the system. Again, this can be done with flow diverters or simply raising the overflow, as well as removing debris ramps that have formed themselves at the overflow. This is when water is coming into the inlet, it's carrying debris, and it drops that debris right in front of the overflow so that it forms almost like a bridge or a ramp that when it gets high enough, water will flow over top of it directly into the overflow instead of going in and getting filtered.
Our next recommendation has to do with the removal of surface crust and deposition. Surface crust was viewed at 18% of sites, and sediment deposition was at 27% of sites. And the issue with this is it can significantly decrease the permeability of surface area of the practice. So what we recommend is just going in and removing these deposited sediments and tilling of the surface to break up these crust layers. For our next recommendation is providing pre-treatment retrofits. As Pam mentioned previously, a lot of these sites are lacking pre-treatment as they were grandfathered into the new pre-treatment regulations for Stafford County. So a lot of these sites are actually lacking any sort of pre-treatment. So what we recommend is that going back to these sites and retrofitting new pre-treatment cells. If space is an issue, there's a lot of new ways of avoiding this issue, like creating pre-treatment cells, which are smaller areas just for the purpose of pre-treatment if space is an issue. So those were all of the recommendations that we are going over, but specifically I want to look over the application of these recommendations, specifically looking at requiring extra stabilization of side slopes greater than 25%, ensuring adequate elevation drop at inlets on offline systems, and preventing short circuiting. All three of these recommendations have to do with the design and construction stage. And these are so significant because these are issues that we could be fixing now through the change in regulation of how these sites are created. And these changes can prevent long-term issues within these sites and increasing the functionality of these sites overall long-term. Thank you so much for listening to our presentation today. We really appreciate you taking the time out of your day to come listen to us. This is our contact information and including a QR code to the full report. Now we'll go to questions. Thank you so much.